Oui, très rapidement. Alors, bienvenue à tous. Meilleurs vœux 2018. C'est notre première série de la saison 5. On remercie Méritis de nous accueillir. Merci Méritis. Donc, on a eu une très belle opportunité de Pierre Sermanet qui travaille à Google Brain et qui est de passage à Paris. Et on s'est dit que si on pouvait organiser quelque chose avec Pierre, c'était vraiment l'occasion à jamais. Donc Pierre va nous faire part de ses recherches. C'est vraiment ça sort du labo, donc c'est la recherche la plus pointue et on est super heureux en fait donc d'avoir Pierre comme invité principal ce soir. On remercie Pierre. On va donner la parole à Méritis s'ils ont...
Ou après, ou avant, enfin, comme vous voulez. Avant, après, comme vous voulez.
Ou alors après.
Merci à tous pour participation ce soir. C'est ravi, c'est là. C'est le premier meetup qu'on a connu.
C'est pas le meetup de l'année, donc bonne année à tous.
Ouais, merci. Et voilà, nous on est très contents parce qu'aujourd'hui, Méritis, pour vous en dire juste un mot, c'est une société de conseil dans le domaine de la banque finance et également dans le domaine de l'industrie. On a d'ailleurs quelques consultants qui sont là ce soir et on les salue. Et ce pourquoi c'est important pour nous aujourd'hui de pouvoir vous accueillir, c'est qu'on a aujourd'hui tout un investissement qui est fait dans le domaine de l'innovation, qui passe par la rédaction d'articles à travers un blog et qui passe par l'accueil de meetup, qui passe par l'organisation de Qatar chez nos clients. Prochainement également cette année, on sera partenaire de 2 hackathons en France, un à Bordeaux et un à Caen. Donc le premier au printemps, le second à l'automne 2018. Donc cette démarche-là, nous on est ravis de la porter. On a envie d'aller toujours plus loin avec des passionnés comme vous pour la mener. Donc si vous avez des idées, si vous avez des envies d'entreprendre, n'hésitez pas à venir toquer à notre porte pour accueillir un meetup ou n'importe quoi. On sera ravis de vous accompagner dans cette démarche. Voilà.
Merci beaucoup. Merci à vous. Alors, juste une dernière annonce et ensuite on donne la parole à Pierre. Donc, comme d'habitude, on cherche des salles et des speakers. Donc, si vous connaissez des gens qui peuvent nous accueillir, idéalement 100 personnes, en tout cas au moins 100. Ou alors, si vous connaissez des speakers qui ont envie de parler de ce qu'ils font, machine learning, etc., qui ont un bon niveau et qui veulent en faire profiter la communauté, n'hésitez pas à venir nous en parler.
Non seulement ça, mais on a un formulaire, donc c'est pas la peine de nous en parler ce soir. Si vous hésitez, vous remplissez le formulaire quand vous êtes prêt. L'idée centrale ici, c'est aussi de faire en sorte de pouvoir gérer tout ça de notre côté. Ça veut dire que on a des dates jusqu'en juin, un par mois. Donc il y a le 14 février, 14 mars, et puis plusieurs autres dates jusqu'en juin. Essayez de faire en sorte de venir un moment ou un autre. Vous avez sûrement des idées super. Venez les présenter à la communauté. Donc voilà, merci beaucoup d'être venu. Et Pierre, you're next.
Ok, merci.
Ok, bonsoir, merci de me recevoir. Je vais faire en anglais parce que sinon ça va être difficile. So I'm going to talk about self-supervised imitation. And this is joint work with my colleagues at Google Brain and USC. And I should point out that Corey is a Brain resident. So Brain residency is a one-year program that we have at Google where people just coming to learn about deep learning. And Yevgen was an intern this summer. So what we're trying to do here is have real robots that can learn on their own just by observing the world and humans in particular. And just like in this example, we just want robots to learn from observation, basically. And there are many challenges to solve to achieve that. So one of the bigger one is how do we get labels? How do we supervise the learning to imitate. So how do we know what to do this kind of imitation? And I'm going to argue in this talk that we don't actually need any labels. Another big issue is that we'd like to use reinforcement learning. And reinforcement learning works well in simulation, but not so much in the real world because it requires too much data. And this is called the sample efficiency problem, which means that reinforcement learning often needs to see millions of samples to learn something meaningful. And by sample, I mean examples. And that's just not practical in the real world. You can't afford to run your experiment millions of times. So another message I want to convey is that we can alleviate this sample efficiency problem by using, in multiple ways, by using self-supervision and by using imitation. So these are two ways we're going to address that. And we're going to do both at the same time. So again, our goal is to learn to have robots that can learn new tasks just from observing humans from a third-person point of view, not first-person, third-person, and without any labels. And the first step we're going to take for that is to observe the world and make sense of it just by observing it passively from videos. And next, using these representations that we have learned in the first step, from a single video, we can now learn a new task and put it on a robot. So this is a preview of the results. So on the left, you have a human third-person demonstration of the task, which is a pouring task here. And from this single video, we have managed to make this robot learn to do this thing. So this is the resulting point. And it seems simple for us as humans, but it's actually pretty hard for a robot. And I want to emphasize that this is a label-free talk, meaning that, so by label, I mean asking humans to tell us what is happening in an image. That's what I mean by label. So we're not going to use any label in the entire talk. It's just going to use raw videos, just like this one. OK, so why do we want to use imitation? First, oh, by the way, I forgot to say that please interrupt me if there's any questions. I want to make this interactive. Okay. So first, we want to use imitation because it's a signal that's widely used in nature as a way to access existing cultures. So, for example, you know, if you've never seen a door before and you're in front of it, you don't know what to do with it. You might spend some time to figure out what to do, how to open the door, etc. But if you see someone doing it, then in a way, you use the culture to kind of bypass the expensive trial and error that you would do if you were trying to open the door by yourself. So that's one advantage. Another is that it's a rich reward function that is just ready to be used in the world. So reward function is one of the biggest issues in reinforcement learning. Is how do you design your reward function? So when you play video games, you get it for free, so that's easy. But in the real world, like it's really not clear what to do. So this is one strong reward function you can harvest in the real world. Third,
what is the reward?
Just observing people doing things. So if you see someone opening a door, it's a kind of reward if you know how to imitate someone. You can just follow what that person is doing. It's a kind of reward, just following, imitating. So third, in robotics, it's often really hard to specify a task, like what to do. You know, if you have to write lines of code to explain to a robot what to do, it's pretty complicated. But if instead you can just record a video of someone doing something, that's just a much easier way to specify a task. And imitation allows us to do that. And finally, the exploration is hard. So by exploration, I mean the exploration phase of reinforcement learning. What I was talking about when you have never seen a door before and you might try random things, or if my goal is to pick up this balloon, if I don't know, I only get a reward when I actually pick up the balloon. So before that, I might just do random motions like this, and maybe by mistake, I actually pick up the ball, and then I get a reward. But this expression phase, you might spend a long time here and actually never actually get to pick up the ball. So this is really expensive. And if you have imitation, you see someone doing that, you can directly go for that and completely bypass the expression phase. And also, so imitation gives you a continuous reward, meaning that this human demonstration tells me that if I go in that direction, I get a stronger reward than if I go in the opposite direction, as opposed to a sparse reward, which is you only get the reward once you succeed at the task. So having a continuous reward is much easier and faster to learn. And also, so like I said, you can initialize your solution directly close to what the solution, a good solution. And also, it reduces the sample efficiency problem. So arguably, the reward design, the expression, and the sample efficiency are the three biggest obstacles to deploying reinforcement learning in the real world. So you hear about DeepMind doing great results for games, but right now it's still kind of stuck in the simulation world. We haven't managed to move to the real world yet. Okay, so so we sometimes use the term learning from demonstration to talk about imitation, but I prefer to talk about imitation because demonstration implies that there's a conscious act, and the TV is not actually aware it is being imitated. So there's no conscious act, and yet the baby is still able to exploit the TV as a signal to train itself. So it's an important distinction because we want our agents to understand the world and imitate without requiring an active demonstration from people. Okay, so why using self-supervised learning? That's because I believe that the revolution will not be supervised. Instead it will be self-supervised. And I'm going to explain a bit better what I mean between the difference between human supervision, which we call supervised learning. It usually means human supervision, unsupervised learning, and self-supervised learning. And I'm going to use this sequence as an example. So this is a human pouring a cup. A liquid into a cup. So if you wanted to figure out what's going on here, if you use supervised learning, you will ask a human to look at one image and then write down what's going on in the image. But first, it probably has to also decide what it cares about, which labels, which categories I want to label. So maybe the human is going to come up with these 5 categories. Hand pose, cup pose, how much liquid is in the cups, is it flowing or not, what's the color. And so for example, the hand pose, it might also want to discretize the variable because if you have such to precisely give you exactly the angle of the cup, it's pretty hard. So maybe we're going to discretize it in bins of like 0, 30, 60 degrees, 90 degrees. But you can tell already there's something wrong with this because, so first of all, it's not clear if these labels are actually going to be useful for the task we care about. Maybe we don't even know which task we're going to do next. Second, discretizing something continuous, we might be losing too much information by having big bins for angles. And it's also really ambiguous how to define the pose of the hand. Right? 90 degrees, what does it mean? Is it with respect to the table, with respect to the body? So instead, you might want to say that, okay, I want to specify all the degrees of freedom of the hand, but a hand is really complicated. So there's so many things to supervise that it's just impractical. And clearly, it's also very expensive to ask humans to look at each frame and repeat that all the time. So instead, we can do unsupervised learning, which doesn't need any humans. But here we're gonna, instead of producing discrete labels, we're gonna produce continuous embeddings. So an embedding is just a low-dimensional vector maybe let's say 32-dimensional vector continuous values. And here, so unsupervised learning is kind of maybe the superset of family for unsupervised methods, and you could include self-supervised learning in there, but sometimes for historical reasons, we often mean supervised learning is actually autoencoders. So that I'm going to make the distinction between the two. So autoencoder means that we take, as input, we take one frame, we pass it through a deep net, and we produce an embedding. And from this embedding, we're going to try to regenerate a new frame. So we going back here, and then now we have two frames I can compare. And if the model managed to produce a frame that looks similar to the original one, then the error is low. If it's really different, then it gets a big error, and then it can backpropagate the weights all the way to the network. So that's why we call it autoencoding. It just tries to reconstruct the input by itself. And there are multiple ways to do this. One is often you have a prior that is applied to this embedding. So one can be a sparsity prior, where you force the values to be mostly zeros, and you have a few of them that are positive. And you could also have a Gaussian prior, where you try to fit a Gaussian distribution, and that's what VAEs use, variational autoencoders. So this is fine, but it works fine for some applications, but I don't think it would work in that case. So instead, what we want to use is self-supervised learning, which is often a stronger signal. So self-supervised learning is often about using extra signals to produce labels that you can teach yourself, basically. And it's often about, you have multiple modalities where one modality is going to supervise another. So for example, you could have depth. So let's say here you had a depth sensor that can see that scene and can maybe segment out this object. Then you can say maybe put a bounding box around the object and train yourself to do object detection in 2D images only. And then you can discard depth. So use an extra signal to teach yourself to do something else.
So sorry, what do you define as depth?
Sorry?
What's your definition of depth?
Depth, you know, a Kinect sensor? Okay, so it's just 3D. So when humans have two eyes, so you can infer the distance of things, right? So either you use stereo vision, or you could have a Kinect that shines laser, and then it tells you that this whole thing is one object, right? Doesn't make sense.
Yes, what is the definition of depth?
That's
just that is
okay.
Yes.
Okay.
Okay. And so what's the point of distinguishing the object you mentioned?
So depth could be used as a way to segment this object,
okay.
Right? Okay. And then you know that this is one object, and you can do detection, right? So another way is you could use time coherence, meaning that you know that these consecutive frames are probably similar, and multi-view coherence. So these are the two signals that we're going to use in this work. You could also use tactile feedback. So let's say I'm holding a bottle and I can feel something in my hand. I can also use vision to say, okay, I'm holding a bottle right now. So what I'm feeling right now is the texture of a bottle, and vice versa. You could also supervise the vision this way. And really, this is really something you have to self-supervise, because no one knows what's going on inside your own body. It's wired specifically for your own body. So the only way to learn this is self-supervision.
What's the point of this continuous embedding? You want to have a low-dimensional understanding of all the things that's going on and the relation between those variables.
Yeah. So that brings me to my next point. One of the points is that learning a latent continuous embedding is much more powerful than something that's discrete and specified by hand, right? Because you can have complex interactions between concepts. Because your embedding is really learning abstract concepts, right? So maybe this one has learned that the concept of a brown liquid flowing from one cup to the other. And that's not something you want to specify by hand, right? And we want to keep it low dimensional because it's easier to deal with, right? So the smaller the space, the easier it is. Okay, so to reiterate, why do we want to self-supervise? So supervised learning is really successful where it's easy for humans to specify tasks and to label it. But in the case of robotics, it's getting labels is not only impractical, it's also really poorly defined. And that's because the world is really high dimensional. For example, this a simple task like pouring has many attributes, like alluded to before. I want to know, as a robot, if I want to run this task, I want to know if my hand is touching the container. I want to know the angle of the container. Is the liquid flowing? Is the liquid? What's the liquid color? What's the texture? Is that foam? So maybe you want to pour champagne differently than if you want to pour water. And how much liquid is in the cup? You really need to know that if you're trying to do that task. And all these details really matter to do this task, and it's really hard to label precisely. So instead, we want our agents to discover what matters and kind of disentangle. So the embedding is trying to disentangle factors, independent factors, if you will. Yeah.
The network is at random at first, right? It's not a pre-trained network on some image net or something.
It is actually, but you don't have to do that. Yeah.
Okay, but how do the network knows what to learn? Like, how does it even know what concept to learn?
Right. I'll explain that later. Yeah.
You were talking about the last point in
Tactile feedback, yeah.
But you cannot have it just by looking the movie.
Right, yeah, sure. Yeah, here I'm talking about the context of agents that have multiple signals coming to them. So,
just by looking, you can have maybe the depth, the time, the multitude of
yes,
ideas, but the tactile seems to be that like you will not learn anything before trying yourself. So it's like you can learn from what you are seeing.
Yeah.
And after, when you try something, there is another, let's say, dimension.
Yes. Yeah. Well, there are some things you have to. You can only learn by trying things, but there's also a lot of things you can learn by just looking at the world. So I agree. Yeah, tactile feedback you actually have to do. Yes.
I have a question. Are you using here just one example to learn?
Oh, what?
Just one example. I mean, just one person doing this.
One video.
Is it only one video, or do you have multiple videos?
So I'll explain that later. We use many videos for without any, not as demonstrations, and then we use one demonstration. I'll get into the details. Okay, so yeah, so there's lots of research on supervised learning that's been kind of evaluated on supervised tasks like ImageNet, and often it just gives you a small improvement, but it's not really convincing. So we kind of take a different approach where we don't really try to do any supervised tasks on top. We're just trying to learn general disentangle representations, and then we just work. We stay in that space and we work with that space. And yeah, we found that self-supervision is a great way to reduce, increase sample efficiency for reinforcement learning. For real-world imitation, there's many challenges. One is the correspondence problem. So you want to get invariance between first and third person views. So something like, I don't know if you know the concept of mirror neurons. So it's something like this on the right, where when you see someone doing something, your brain, there are neurons in your brain that actually fire the same way as if you were doing it yourself. So when I do this, I'm triggering in your brains one neuron, the same neuron as if you were doing it yourself. That's called mirror neurons, because you're mirroring what I'm doing, because you have an understanding of your own body with respect to mine. So you understand what this means for your own body. So this is something you have to learn and discover. And that's pretty hard. So like I said, supervised variables, we don't even know which ones matter. It's hard to handle ambiguities and continuous labels. It's hard to collect at scale. A reward function is very hard to design as well. So in this case, we had a robot that was trying to learn to open the door. And to know if it succeeded, we put a sensor on the handle. It's an IMU. So this is obviously a lot of work, a lot of engineering time that it's just not going to scale. So instead, we like to just use vision to understand if it worked or not. Like I said, it's how do you make your system sample efficient? We'd like to learn new tasks quickly as well. And we like to avoid using kinesthetic demonstrations. So kinesthetic means it's a physical demonstration where someone is going to move the arm by hand and show it what to do, record it, and then replay it. That's a kinesthetic demonstration. But that's also a lot of work. So we like to avoid this. And we propose a unified solution based on time-constructive networks that kind of addresses, to some extent, all these issues. And in prior work, we showed that exactly this thing where we had we tried to learn unsupervised perceptual rewards, meaning that from a human demonstration, we want to output a reward function that goes from the minimum to max that increases over time as the task is being completed. So this is what we obtain, works well. And then we feed that to the robots, and we remove the sensor on the door handle, and then it learned to open the door. So we replaced the physical sensor with a visual reward function. Now, one big caveat is that this still required the original work we picked up required a kinesthetic demonstration for it to work, meaning that it needed an approximate solution of going to the door handle, opening it. That works about 10% of the time. And then using that reward function, we go from 10% success to 100% success. But that's still we want to get rid of that demonstration. And in the work on the chapter, we actually don't need that anymore, and that's a pretty big deal. These are more results on this. So on the top, you had a human demonstration, and you can see that it starts to increase as the hand gets close to the door handle, and then when the door gets open, it increases again, and then you get full reward for opening the door. This is an example showing that when the hand is approaching, you get a bit of reward, but then when it goes away, it goes back down to 0. So it does what's expected. Now, when the robot does it itself, so the robot is looking at it itself. The model has actually never been trained on robot hands, so it doesn't trigger here because it doesn't recognize its own hand. But it does trigger when the door is being opened. And that was enough to, even though we didn't get the full reward for the robot, that was enough to actually learn that door opening task. And this is one more example for pouring. So this is the entire training set. That's about 12 videos. And what we want to show here is that you can learn a pouring task with really small amount of data. So that's what I meant by learning quickly. You see a few examples, and then you can do it. And these are some results. So you see increases with the amount of liquid, basically. Here, even though there's no liquid, it's a bit noisy, but it stays low. And the last one already has liquid, so it's already high. So again, it does what's expected. Okay, so for time-constructed networks, we're going to make use of multiple videos. So on the left, you have 2 views happening at the same time from a first-person view and third-person view. And you can do this pretty easily with 2 phones. So that's what we had here. We have 2 phones and a off-the-shelf app on the phones where you just hit record and it synchronizes the views. But you can also do this with a laptop where you just plug in multiple cameras and then it just synchronizes the views. And you'll notice that the third-person view is moving around a lot. And that's on purpose because we want to increase invariance to viewpoint, to scale, occlusion, and motion blur. So think of it as first person view is what the robot is going to see, and third person view is it's going to see of itself, and third person view is what it's seeing of someone else. So it needs to be able to do it from any angle, basically, and any scale. But so the way it works is what we're going to do. So we have our two views here that are synchronized. What we're going to do is trying to map different viewpoints to the same location. So we're trying to say that these two blue frames should be represented, should have the same representation, regardless of the angle. But the red frame should be different. So the concepts present in the blue frame should be the same, but the red one should be different. And you can do this using metric learning losses. So metric learning means that we have an abstract space, and we're going to have points in there, and we're going to push them apart. You're going to try to organize the space, basically. So one metric learning loss is the triplet loss here. So triplet loss just means that we have three points, three inputs, and we know how they relate. We know that, so on the top right, you see, so they're called anchor, positive, and negative. So let's say that this one is the anchor, this one is the positive, and this one is the negative. So the center is the anchor. And in this case, we have the positive is further away in distance than the negative. But actually, I just said that we'd like to have these 2 points be closer to each other than the anchor and the negative. So all we need to do is actually to push, to pull on the positive, so that anchor and positive are closer to each other, and to push on the negative. And we want it to be beyond a certain margin range. So if there's a big enough distance between the positive and negative, then we're happy with stuff. So we just want to order things. We just want to say that these two frames are more similar than these two. Okay. So what kind of, and I should say that, of course, this goes through a deep network. And what you get right below the triplet loss is what we call TCN embedding. So it's this 32-dimensional embedding where points exist, and their distance is what defines how they relate to each other. And so what do we expect to learn from this setup? So what kind of representations should we have? So there's kind of a double effect going on here. There's two constraints being imposed on the model. One constraint is along this direction. The model has to understand, to have these 2 points close to each other, it has to understand that what is common between these two frames. Because we know they're at the same time. So we know we're looking at exactly the same thing. So we have to abstract away what is different and pull together what's common. So in this case, it has to abstract away the background, which is really different. So even though they look really different, we want to say these are the same frames. And along this axis, it's kind of the opposite, where the model has to understand what's different between two frames, even though they look quite similar. So because these frames are right next to each other in time, they look really similar, and the only way for the model to push them apart is to understand the tiny differences. So in this case, to do that, the model could just model the amount of liquid in the cup or the difference in handfuls. And having these two constraints being trained at the same time is really a strong signal. So the more simultaneous signals you have, usually the easier it is to learn something, because there's only so many ways to explain these two strong constraints. If you had only one, then there's many ways you could actually explain it, and you could have a trivial solution maybe. So here we have an embedder that learns to explain changes over time, and is also invariant in viewpoints. So that's a great way to discover general concepts without any particular application in mind. This is really general. We don't care about the task really. But it's also the fact that we are viewpoint invariant is really useful for imitation as well. And the attributes that we said were difficult to label are exactly actually the ones that we expect to discover. So this setup is really going to discover, how much liquid there is, what's the hand pose, and so this is what we need. And once the embedding is trained, we can use that on the real robot to actually do the imitation. Right. So again, this model is not specific to robotics. It's not even specific to vision, because you could have, instead of views, you could have different things. You could have sound, you could have tactile feedback. So this is not really specific to vision. And while multi-view capture is not ideal, ideally just one view would be easier, right? It's actually, I said, just as a temporary shortcut that we can use to make progress, because once we have a rich embedding, there are many things we can do on top. And just this is a kind of emulation of emulating multi-view capture can be done later once we have more complete and situated robots that can actually remember where they are, so they could move their head around and then get some kind of multi-view capture and then do some kind of TCN training. But this requires obviously to have a full system engineering. So in the meantime, we can just use this little trick to make some progress. And also capturing data like this is really easy, and we don't actually need that much data, because for this task we only use 40 minutes pouring, which is pretty small. Yeah.
Several things. There was which distance do you use for it? And you try more than 32 dimension.
So what do you mean by which distance?
L2.
Do you mean for this?
When you compare the loss.
Well, there's multiple ways. So this is interpret loss. Yeah, you could use L2, but I think there are other ones out there. But we didn't actually use interpret loss. It's just easier to explain. But there are other metric learning losses. So actually, all of them, they kind of work similarly, so it doesn't matter too much. But yeah, you could think of L2. Yes.
Have you tried to visualize the embeddings?
Yes, I'll show you later. And so we also have a single view version where it's the same idea, where you have your two blue frames where these are just neighbors in time, so we want to pull them together. And any frame that's beyond a certain range that's a factor of this one, we use as negative. So that's one more that I'll compare it again after, and we'll also compare against this baseline, which is called shuffle and learn. And here the idea is that you have a sequence of frames, and we can decide to shuffle the order of frames or not, and then try to classify if the frames have been shuffled or not. So this is also self-supervised learning. So that's the baseline we used. And here we have some results for imitation. So we call it nearest neighbor imitation, because on the left we have a video that we try to imitate. On the right we have a different video doing the same task. But basically the model, so there are three models here. And what the model is trying to do here is that for each frame on the left, it has to pick the frame from the video on the right that most corresponds to the one on the left. So if it's doing the exact same thing at the same time, it means that the model captured a really good functional understanding of the scene. And we find that often multi-view is the most stable results we've seen. So you can see single view and shuffle and learn, they're more noisy. This is a failure case where initially, yeah, so most of it is good. So the hand is imitating well. But at the end, it kind of reverts back to going to the empty cup. And it should really be full. It should stay full. So that's one error. Actually, now I think we don't have this problem anymore, but that's one thing that can happen. And these are more recent results. So yeah, the videos before were from an older version of the model, and this is really a recent one. And it's much more stable. You see less flickering and less noise. Just a little bit.
For the multi-view, did you only use multi-point of view sources or just consider the stereograph views?
Yeah, so we haven't done stereo where you have a fixed baseline. So we actually have really different viewpoints because that's a stronger signal. But it is possible that you could learn something from a fixed baseline.
And does
so we haven't done that yet.
And does the point of view of third person is grounded in the neuron imitated in neurons idea, or it's just because it's easier to task? Sorry for the English, but
is it grounded?
that in our brain we have someone cells which try to imitate what does it look from a third person view, and that's why you try to replicate.
Yes.
Going in the same idea, do you think it's possible if you learn from two different views to at some point from one single view and the first image to generate the whole sequence from the second point of view? See what I mean? Like learning translation in space, for example, or a change of point of view.
So you mean, I think it's called parallax, when you move your head, when you see multiple views, right? Is that what you mean?
Could you make a generative model? I think that's the question.
So I'm saying you learn different views of the same sequences,
and
then starting from, the starting points of the new sequence, and you have only one information, can you generate the other one that could be
we haven't done that, but
you get,
if the model is able to be viewpoint invariant, then yes, there's no reason it could not do that. So these are results before we actually tried on real robot. We wanted to figure out if the imitation still works with a robot hand. So this is just me holding a robot hand, and the model has never been trained on robot hands before, and we want to see if it still works, and it kind of works okay. And I think that's probably because it's kind of grounded by the object, so you can still use that as a cue. So this gave us confidence that it should work on the robot. And so this is what we did next. So again, the first step is to learn representations without any labels from two multiple views. Then we get this embedding space here. And we take that embedding and we feed it to the reinforcement learning algorithm. So meaning that we have this one demonstration video that it's crashing. Let me try. Okay. Okay. So we have this one human demonstration. We encode it through the TCN that gives us a trajectory in embedding space that we need to follow, and we try to follow it with it's called Huberlos, but it's similar to L2. Because the robot is also being passed through the TCN. So it gets its own trajectory and just trying to match the trajectories. And so initially, so iteration 0, okay, so this is the last one. Actually, iteration 0, it tries to do this random motion. It doesn't know what to do yet. So it does random exploration. Iteration 3 starts to cut to the left and forward a little bit, and then puts a lot of beads around it, and then iteration 9 it manages to do it, and that's pretty fast actually. So again, this is the final. If you haven't seen, well, this is the final policy that we learned from a third-person perspective. And again, this is really easy for humans, but it's pretty hard for robots. So we took this approach, we applied it to a different task, but it's the exact same approach. This task here is we have to move a plate from one dish rack to the next. We have two dish racks in simulation, in VR. And we have two views here. Again, we pass it through the embedding. We learn a good representation of what this is. And then we learn from a single expression. So we have a single demonstration on the left from a third-person angle. So we have someone that does the demonstration, and then on the right, we learn a policy to imitate that.
Based on synthetic images.
Yes.
Okay. Why not film it with a camera? Some real. Is that not easier? Or why did you?
This was just to. This was actually before we did the real robot. It's just to experiment. Yeah, so you can see in this task, what's impressive here is that the TCN managed to discover everything it needs to know about the gripper. So the pose and open and closing, even though we didn't tell it anything, we just gave it pixels and it figured out the opening and closing. And that's really important for this task because when you pick up the plate, so initially you see it drops the plate. But at the end, it knows when to open, close, and then drop it right. And if it opens in mid-air, then it's going to fail at the task. So this is the final policy. We see these are multiple runs of the same policy, so it's slightly different every time. And also, yeah, it's not exactly the same because here we don't have the arm. So visually, it's quite similar, but there's also the arm here. It's a little bit different. So yeah, so I want to repeat that the only inputs to the systems, all the systems using this talk are just videos. So on the left, we have this big collection of videos, not that big actually, it's like 40 minutes. Videos that are not just positive demonstrations, but also random interactions, things that we might need to know when we actually try. So for example, here, we see we don't just do that demonstration thing, we also move things around, move plates, we actually turn them upside down, I think.
Because otherwise you would give only an indication on what's around the real solution, but you would be lost
Exactly.
otherwise.
Yeah, you need to model as much as possible of the space. Because if you drop the plate and you don't know what's happening, right, you're screwed. So so that's what I mean by unstructured. It's like it's just anything. You want to see as much as possible. And we learn from that, and then we only learn the task from a single video again. Okay.
If I understand correctly, the models you learn are task specific. So here you showed us two tasks.
Yeah.
The dish moving task and the.
Yeah. So in this case, we train one model per data set.
So both the TCN and the RL policy, they're both task specific.
In this case, yes, but I'm pretty confident that when we scale up to more tasks, it will just work fine.
Oh,
yeah. Yeah, so we found that multi-view is pretty rich signal because we managed to learn pretty strong representations. And one evidence of this is that the training curve, it trains about 20 times faster than the single view, the two single view baselines I mentioned, even though it was trained on the exact same data. The only difference is that the single view ones didn't make use of the time synchronization. So the fact that it trains 20 times faster means that it's just much, like I said before, the more constrained, the easier it is to learn, and the faster it is to learn. And we also have quantitative results. We have two metrics. One is the video alignment error, where we have two videos of a positive task, and we try to see how well they're aligned semantically. And that's this one. And the other one is attributes classification. So we label by hand some attributes, like these guys, the ones I mentioned before. Is my hand touching container? What's the distance? Is that liquid flowing? And we evaluate how accurate the class. It's a nearest neighbor classification. So that gives us an idea how well these attributes are modeled. And we found that the multi-view baselines are pretty similar. Shuffle and learn and single view are pretty similar. And multi-view, so we actually tried 3 different triplet loss, metric learning losses, and they perform somewhat the same. But there's a pretty big gap between single view and multi-view. Yeah, so one question that might arise if you try to do learning without any labels is when should you stop training? When do you know you have good representation? Should you trust that your validation error is, you can stop when the validation error is at the lowest, or is it possible that the classification error is actually gives you a better idea of when to stop? So we tested that, and in our case, we found that it's actually pretty similar. So it's slightly better with the classification accuracy because that's what we wanted to see here, but actually you can just use the loss and stop when it's at the lowest, and that's fine. So that's good news, because otherwise you need to label something by hand to train your model, and we don't want to do that. And the quantitative analysis of the polling task is here, where this is, so we actually measure how much weight we find in the target cup. And in green is the maximum weight that you can expect if you succeed at the task. And in this green curve here is the multi-view TCN. So as it learns to do the task, it gets more and more bits into the cup. That's clear. So if you are up here, it means you managed to do that task. And we found that, surprisingly, only the multi-view TCN managed to actually learn to do that task. We couldn't do it with the single view one. So that kind of tells us that multi-view is a pretty strong signal that we want to use. Okay, so now we also used TCN for pose imitation. So this imitation here, so the robot on the right is trying to imitate the human on the left. And this was entirely learned from observation without any labels. We didn't tell the robot what to do. It just figured out this mapping by itself. And we didn't train on sim data. This is just for visualization because it's easier to run on the sim than running on the real robot. So even though we're showing sim here, we'd actually train on real data. And so the way it works is we have multiple self-supervision signals. So we have two TCN supervision happening. So one is happening on multi-view video of humans doing random motions like this with one arm. So this is trained by itself. Then we do the same for robots doing random motion as well, trained on itself. and they all share the same model. So things that are learned here, they also share with this guy. But we don't give it correspondence between the two ever. And the last one is we call it self-regression because it's a robot. We're trying to map an image of a robot with the joints it should output to do that pose. So think of it as something like this, where the robot is looking at itself in the mirror and doing random motion and gets an image of itself and knows the internal configuration of its body. So it knows this image should correspond to this configuration. So now when it sees itself, it can imitate itself. And next, yeah, so this is entirely self-supervised, end-to-end, meaning that there's no explicit representation of pose. So often there's people working on matching key points on the body and matching it with in frames. But here we argue that we actually want to bypass that thing. It might be useful for some applications, but in our case, it hurts more to try to specify because it's not even clear how a human body relates to a robot body. So it's better to let the robot try to discover it by itself. And we want to do it end-to-end. So there's no human intervention at all. So again, the way it works is so we have this deep model that produces the embedding that we train with the two time compressive losses. Then on top of that, we have a joints decoder that, given this embedding, produces the joints that correspond to that person. And then we feed that to the robot, and then it can imitate. So when you look at itself in the mirror, there's a robot here. But somehow the TCN has managed to find the correspondence between humans and robots. So if you actually put a human picture, then it thinks it's itself, and then it can imitate itself. So that's kind of, it feels a bit magic, but we're not sure exactly why it's happening. I think one theory is that if you have two somewhat low dimensional manifolds, you try to have two manifolds. You have one manifold for humans, one for robots, and they try to coexist in this low-dimensional space. So if it's really small, then the most efficient way to use the space is to really align the two manifolds. And also the fact that even though they look pretty different, there's a different number of joints, there is some visual similarity that can help drive this alignment of manifolds. So this is what I think is happening, and this is what makes the imitation possible. And this is the same on the real robot, so it's a little bit less reactive than the simulation, but it gets the idea. And yeah, like I was saying, if you look at this squatting up and down motion, on the left you have many joints happening for the human, but on the right there's only one joint for going up and down. So how do you go from many joints to one joint? How do you specify that by hand? It's just not clear what to do, right? So that's why we don't want to label this by hand. We want to discover the mapping. Okay, here's a failure case. So going up and down like this. So it kind of gets the vertical motion ID, but it's really noisy in the shoulder joints here. And I think that's because we didn't have that much data for this kind of motion. And you were asking about embedding representation. So this is a Disney 2D representation of the vector. It's actually 128, I think. So we fold it to 2 dimensions, and we find that so all these 3 frames come from the same location, and we find that neighbors, they tend to show similar codes. Same here, these 3 guys, they come from the same location here.
What does the color represent? So clustering?
The color is, I think it's different people.
Okay.
Yeah. So actually, that's what we show here. This is before training. We have different people. One color is one person. So you see that it's clustered by instance. But after training, it's all mushed together, and it's actually clustered by pose. Okay, so who knows the cake meme? Yeah, okay. Yes, so the cake, this is kind of a controversial meme that's happening at NIPS, started last year. But now this year, everyone puts it on the site, so it's actually accepted. So this is just a picture trying to convey the idea that most of the learning should be unsupervised. So the biggest part of the cake should be unsupervised. And the cherry on the cake is the reinforcement learning part. So it doesn't mean that reinforcement learning is less important. It just means that it should do less work because it's a weaker signal. So most of the work, most of the disentangling should be done by self-supervised learning. And actually, reinforcement learning does a different type of learning. It's something where you actually interact in the world, and it's maybe less learning, but it's a more abstract type of learning. So they both complement each other. And why we're talking about this is because there's a lot of work happening in reinforcement learning, but not too much in unsupervised learning. And this is just a reminder that research should spend a lot of time also looking at the cake, because that's really what enables us to do reinforcement learning in the real world. And in our case, so this is actually exactly what we did. So we have a cake where the TCN is doing a lot of the leveraging. It's just disentangles. It does most of the work. And then the RL on top of that now can actually do the learning. So if we had to learn the features from RL by itself, it would just not have been possible. So this is only possible, the deploying task on the real robot is only possible because of this big self-supervision here. And because RL is a weak signal, that's why it needs so many examples. So either you have enough samples that you can train your RL, but if you don't, like in the real world, then you have to make it easier for the RL. It should be really low dimensional and well disentangled inputs that you give to RL for it to work. Okay, so to reiterate on sample efficiency, these are the 3 ways that our approach helps with sample efficiency. First, by disentangling the world beforehand, then RL doesn't need to do much work. Doesn't need to learn representations from scratch, and then you just need to do these little actions to learn how to navigate that high-dimensional space. Second, because our agents perceive a continuous reward, the imitation is a dense trajectory. That also makes it much easier to follow than if you had a sparse reward. You only get one bit of reward at the end. And last, by doing direct imitation, if you have to pick up this thing, you can bypass the exploration phase and just go straight for the solution. So these 3 ways together, that's what allows us to do real-world robotics. And future work, so there are many things we can do. One limitation right now is it tends to focus on the most salient cues. So for example, the hand is not something that moves all the time, so it's pretty strong signal, so it could decide to just model the hand pose and ignore the rest. So we're working on that. I think we have found a way to address it. We'd like to scale up TCN presentations, have more data sets, see if it works. Many tasks. Maybe in this whole room you could do many things, and see if you can have one embedding that can model all of this. Do more general RL on top. Use different modalities that I mentioned. Sound and maybe tactile feedback could be used as well. And also one question that came up is, could you use stereo vision to do some kind of contrastive learning like we do? So is it possible that humans actually do that? That's possible. So that's something I'd like to explore as well, I think. And in conclusion, so with time contrastive networks, we showed that first we managed to learn a self-supervised understanding of the world with no labels. And we use it for real-world tasks, entirely from third-person view of humans. And by doing that, we managed to address the correspondence problem, not using any labels, not needing to design a reward function. We made the RL sample efficient. We quickly learned new tasks, and we didn't need a kinesthetic demonstrators. So all these challenges I mentioned earlier, we managed to address them here. And the paper, data, and code are available at this address. Thank you.
Donc, merci d'avoir tenu le temps. C'était les 3 quarts d'heure multipliés par 2 que tu nous avais promis. Ouais. Des questions pour Pierre? Allez. In English, French, whatever.
Yeah, how does the deep network for TCN look like? Like, what's the different layers?
So you can use anything you want. We actually use the inception model where you just cut. I think we cut it at mix C or something. So you cut a few layers on top, and then you put your loss on top, and that's it.
Okay.
Yep. In terms of performance, how much CPU or TPU do you need to train this sort of stuff?
I think we train, so the point test, we train it in maybe 24 hours on one GPU.
Okay.
But we also have TPUs. It trains much faster. I don't know if I'm allowed to say how it trains faster and faster.
Okay, faster. But you're not allowed to say.
Iteration. Sur le slide, c'était.
Yeah. It trains with 50,000 iterations, but it's also pretty good to let it go to 1 million.
Okay.
Do you plan coupling your methods with some kind of intrinsic motivation or curriculum learning, for instance, in order to make the robot not try to imitate stuff it cannot yet? I am thinking of the work of Pierre Sermanet, for instance.
Yeah, I'm working on that right now. Yeah.
Yeah.
Actually, in the middle of your presentation, some value from 0 to 1, you know, the curve, which was interesting. I'm afraid I could not really understand how you are doing that. Is it something that you are doing manually? Yes, this So the red curve is something that is made automatically, or
Yes.
something that you are defining?
No, it's also unsupervised. So yeah, I didn't explain how it works, but it's first finding it's using features, pre-trained features from Inception. So you pass your images through a network, and then you have this somewhat low-dimensional representation. And in that space, because this is a more abstract space, that's where we want to compare frames. So in that space, we can cluster. Here we're looking for we're trying to segment 3 different segments in that video. So we look for the frames in embedding space that are the most similar as 3 different segments. So we found that this segment is the most consistent, and then this one, and then the last one. And we use that to self-train a classifier that's going to tell us which phase we're at right now. So that's what gives us the reward function.
So you define the faces, but you sort of bootstrapped it.
You define how many faces you have, but
Yes.
then it finds it.
Okay.
Yeah.
Have you tried to make some tiny changes in the embedding that is built so that you can test what has been learned?
We did try that at some point. It was too early, so we haven't tried again. But yeah, I'm expecting that you will find. Actually, we have, and you do find if you put it to a 2-dimensional space, you do find that for the pouring motion, you see it going in one direction, and then when it pours, it goes in the other direction. So if you actually move that thing, you could make the video go back and forth.
But you could like map each bit on the embedding and just better understand what it corresponds to.
Yeah, so
it requires a lot of
yeah, so you mean wiggle by hand each dimension and then see what happens in inputs, right? Yeah, so we did that a little bit, and that's only going to tell you so much. So when it's 32-dimensional, maybe there's there might be some interactions, complex interactions as well. It's not clear that each value is going to be independent from each other.
Plus fort. Moi, j'entends pas.
Number of angles.
Yes, that has been considered.
Can you repeat the
Okay,
question?
you mean for the classification accuracy?
Can you repeat the question?
He's asking how many angles were in the classification accuracy metric, which is yeah, continuous angles. So I think we had 5 different angles: 0, 30, 60, 90, something like that. But we don't care so much for that. This is just a way for us to know if it's doing something sensible.
Is it a good factor or a good tree?
A good what?
A good model. Is the number of angles a good factor?
We don't actually train on this. This is just to evaluate. We never use any labels. This is just for us to know how well the angle of the cup is modeled by the embedding. But we don't actually use that to train.
Okay. No question?
So you got a lot of different embeddings from different tasks, right? Did you always use the same size? Maybe some tasks require less embedding space, some require...
Yeah. We used 32 for the pouring and the dish rack thing, but I think 16 was working well as well for the dish rack. And actually, if you go down to 2, it somewhat works too. So,
2.
Yeah. I mean, it works. The imitation looks sensible. We haven't actually done it with the real robot, but I feel like you could do decently.
Yeah.
Have you tried to do some kind of transfer learning?
What do you mean by that?
Taking a model that has been trained to one task, pouring a cup, and transferring it to another task.
Right. Well, so like I said before, we need to kind of have seen something that's going to happen for it to understand. So you can't really do that. But this is actually a kind of transfer learning, because we go from one robot's body is different modality than the human body. So there is some transfer happening.
What does Google use for robotics? Is it ROS like everybody else, or is there some sexy robot tool?
We just use, this is off the shelf, commercial robot Fetch.
Okay.
And we also use the Kukas. We don't use anything specific.
Okay.
And did you try like a cascade of imitation learning, like the second robot learning from the third one, and see how the loss of information occurs? Like,
Not yet, but that's a good idea. Yeah.
Okay.
Une autre question?
Une ou deux questions et puis on.
Ouais. Ou pas? Ouais, vas-y.
Just small question for the track. So do I understand correctly that somehow you managed to handle the collision without like specifically like physical collision of objects inside the model, or like you kind of hardcode the embedded on your side?
By physical collision, you mean when it's touching the?
Yeah, for example, not to crash into table or.
Well, the RL I guess knows a little bit about that. It knows that it cannot just go straight. It needs to go out, right? But I'm not sure if it's because it's if it's tried to move this way when it was at the track, or if it's just following the imitation that's going on. So I'm not sure. But the TC in itself is kind of frame-based. It doesn't really have a sense of physics yet. But if you made it temporal, then it could actually learn physics.
Vous essayez une dernière question? Ouais. Allez, tiens.
Did you try to use some kind of approach from optimal transport to learn the loss?
Optimal?
Transport.
Transport. What? I don't know what it is.
Like, distance, passage time distance or something.
Okay.
Getting different matrices?
Try use this for learn a different kind of loss.
No. Again, we tried different metric learning losses. I'm sure there are more you can use. Yeah, no, but we can do it.
Ok, donc c'était la dernière question. Merci encore, Pierre.
Ok.
Le prochain meetup, c'est mercredi prochain. Voilà. Donc, on va envoyer une sorte de newsletter pour le début de l'année et on parlera de tout ça et puis d'autres choses qui vont se passer. Merci encore d'être venu. Et puis, il y a des petites... Super.